Okay, so the first thing we want to talk about is what happens when you're standing, if this is Earth, right, and the center is there. What happens if you're standing here? What is your radius while you're standing on Earth? So that would be one Earth radius right there. So on the surface, you are one Earth radius away. So it's important to look at the relationships that happen here, because if we know this is the equation for gravity, right here, um, let's take a look at some of these relationships real quick and see what happens. If I were to double one of the masses, or actually double, that's actually doubling the product of those two masses. If I do that, what I'll have to do is I will have to double the force of gravity will also double. This makes sense. The one where some people struggle with a little bit is what happens if I double the radius, or the orbital radius. So if you take a look, if we moved our little guy one Earth radius out here so that he was now located here, we're effectively doubling the radius. Well, I'm not doubling anything in the numerator. I'm doubling something in the denominator. But let's not forget that that radius is squared. So this is actually 4r squared. So it does not decrease the force of gravity by a factor of 2. It decreases by a factor of 4, because this is the inverse square relationship. So, in other words, if I, oops, that's not what I wanted to delete. If I multiplied the radius by 3, I would effectively be reducing the force of gravity by a factor of 9, because it's 3r squared. Now, if I divide the radius by half, the inverse of 1/2 squared is 4. So I would be multiplying by 4. So it's not just an inverse relationship, it is the inverse squared relationship. Okay? Now, that's important to realize, because what we also need to talk about is what happens. Why do we experience the same gravity over and over and over again? So if you take a look here, all of the gravity that we've been calculating, we've done so on Earth. So the mass number 1 here is usually just the mass of the Earth. And so this radius, we're always usually on the surface, this would be the radius of the Earth. So if you were to take a look at these things right here, that part of the equation, they will come out to be the exact same thing every single time, right? And this is on the surface of the Earth. And so what you end up with is, if you plug in the actual values for the mass of the Earth, not the rounded off values that I gave you, and the actual radius of the Earth, again, not the rounded off version that is on your equation sheet. But if you plug those in, and the value for g, which is a constant which never changes, what I've circled in red here, this always comes out to be 9.8 every single time. And the units on that would be meters per second squared. Or the equivalent units, the exact same thing, would be newtons divided by kilograms. Let me get rid of that for you. So meters per second squared or newtons per kilogram are the same thing. Like if you look at this equation, F equals ma, well, acceleration is equal to force divided by mass, which would be newtons divided by kilograms, or meters per second per second. Those are the same thing. All right. And if you remember, a newton is actually a kilogram meter per second per second. So a kilogram meter per second, and all of this is divided by a kilogram. And so you end up with those canceling, you're left with meters per second per second. So a meter per second squared or a newton kilogram is in fact the same exact thing. Okay. Now, we always get 9.8. So back to what I was originally talking about there. Let me see if I can get all this erased. Is we always get 9.8 when we divide those things out, or which has been our acceleration of gravity. So that's why we've been allowed, that's why we've been allowed to, at this point, use this. We've been allowed to use this because this part right here that's encircled in red, that part right there, always comes out to be 9.8 when you're on the surface of the Earth. So when you're on Earth, as long as you know what G is, this is a perfectly valid equation. So as long as you're able to calculate this little G right here, this equation is perfectly valid. Now, the thing is, how do we get that little G? Well, little g is the acceleration of gravity or gravitational field strength. And so I'm going to clear all this real quick. And so how do we get that? So what ends up happening is you have some object that has some mass. We'll say this is Earth, right? Has some mass. It creates what we call a gravitational field. Well, we know gravity is a field force because it doesn't actually have to touch you. So what it does is it creates field force lines like this, and it attracts any object to its center. And so anything with mass will do this. So you create a gravitational field because you have mass, and so you're creating a gravitational field. Now, how strong that gravitational field is depends on where you're located at it, because we know that Fg is equal to mg. We also know that's equal to big G times the mass of the object creating times the mass of whatever object is put in that field divided by your radius squared. Well, what ends up happening is if you divide each side by the masses cancel, and we end up with this equation. Little g is the big constant times the mass of the object creating the field divided by the radius from it squared. This is what we call gravitational field strength. And the units we get on this are newtons per kilogram or meters per second squared. And so it really depends on context. If we're talking about gravitational field strength, we use these units, the newtons per kilogram. If we're talking about the acceleration of gravity, then we use these units. They are the exact same thing. You calculate them the exact same way. And so this is how you calculate lower g or little g. And this is how we did the little g in my previous explanation. And so if you calculate this little g, then using this equation, Fg equals mg, is totally acceptable as long as we use that for little g, wherever it may be. Now, you'll notice that the relationship, what you see here in gravitational field strength, the relationships of how it changes are very similar to gravity, except for one little thing. Um, you'll notice that these two things right here are not going to change ever. G is going to always be the same. The mass of whatever object is creating the field is not going to change. So let's say that's the Earth. That's not going to change. What will change is your location within that field. But you notice it's the exact same relationship I was showing earlier. So if you double the radius, what do you do to the gravitational field strength? Well, you divide by 4. The same exact relationship as we had before. And so on the back of your problems that I gave you for this unit, there's a table, and there's an object on Earth that has I think the weight is 24,000 newtons. On Earth, little g is 9.8. So you know the gravitational field strength is 9.8 newtons per kilogram, or meters per second if you're talking about acceleration. You can do an Fg equals mg very quickly to find the mass of that object. And then there's a table where we've changed all of those locations, and we want you to calculate the weight at the new location, calculate the gravitational field strength at the new location, or the acceleration of gravity at the same location. What's nice there is the gravitational field strength and the acceleration of gravity are the exact same thing. It's just context where we change the units, and so that's not going to change anything. Also, the mass of the object should never change, because the mass is just how much stuff there is. That's not going to change. So the mass of the object will be whatever it is on Earth. And so that should be pretty simple to find. But what I do in that table is I give you all the different ways I can describe changing the radius or changing the location. Be careful, because if we come back here, remember this from center to here, that's one radius. So if I say we are one radius above, right? One radius above the surface, that is effectively doubling the distance. If I say I'm 2 radii above the surface here, that would be tripling the radius. So just be very careful. There's a lot of nuance in